All right, hello and good morning, everyone. So first of all, let me thank the organizers for putting up this wonderful conference. Good to see all of you here, and it's great to be back at ICTS finally. Okay, so it's Friday, so I think most of us are already sort of in a relaxing mood. So I would try to keep my talk simple, and maybe we'll try to finish also quickly. Let's hope for that. Okay, so what I'm going to talk today is some of our recent work where we're trying to understand transport properties in quasi-periodic systems. So right away, I should acknowledge my collaborators. So Madhumita is a postdoc in our group at IISER Pune, and Prasanna needs no introduction, is already here. And I'm going to talk about two set of works. So one is this one, which I'm going to primarily focus on, and the other one is just recently put up on arXiv. Okay, so the title already says about quasi-periodic lattice. So the question is, what is that? All right, so what are quasi-periodic systems? So quasi-periodic lattice systems are nothing but they lie in between of a completely periodic system and a completely disordered system. So it's something in between. So we already probably in condensed matter, we have studied a disordered system in quite detail, which are essentially gives you physics of Anderson localization. So we already know if you put disorder in 1D and 2D, no matter what disorder you put, you immediately get a localized, all states gets localized, and 3D you get states with mobility H. But that's a completely disordered lattice. Whereas the quasi-periodic systems are neither periodic nor disordered. So as a result, you get some interesting physics. For example, you could see delocalization to localization transition, even in 1D. And also you could actually create something called as mobility. So I'm going to talk about that. So that's kind of interesting. Okay, so we are going to understand these quasi-periodic systems and particularly the transport properties. Okay, experiments, yeah, now there are like multiple experimental realizations where essentially with you load ultracold atoms in optical lattices, which are quasi-periodic. So there are many experimental realizations, and there are studies which tries to understand the underlying single particle states, understand many body localization, transport properties, and as well as there are recent activities to understand also these transport properties in these systems by connecting like two external baths and making it an open system. Okay, so there are many such studies that are going on. Now, what kind of questions we got interested in? So we tried to ask the question that I have this kind of a quasi-periodic lattice, let's say, and let's say that I'm not going to probe directly, I'm not going to see directly the lattice, but I still want to understand the properties of this lattice or the states that we have. And for that, to understand that, let us, if I don't see it directly, what can I do is let me bring a qubit and try to couple it with a particular site of the lattice and try to see what information gets captured in the qubit. So essentially qubit is like a probe, and this is very much in line with what Sebastian was talking yesterday, where he's like putting a Rydberg atom in a BC environment. So it's and reading out through the Rydberg atom. So it's essentially in a similar idea where you are putting a qubit in somewhere in the lattice and trying to understand the properties of the lattice. And we actually go beyond putting a single qubit, but in fact even bring two qubits, and that actually helps you to understand the underlying transport properties. So if you really want to understand transport, you need to bring two qubits and try to see some kind of correlations between this qubit, which gives you perfect information about the transport. So this is what we are up to. We just simply ask, we don't look at the lattice, but look at the qubit and what information we get about the lattice or the transport. And the second part, which I'm not sure if I'm going to get time. The underlying transport properties in this kind of quasi-periodic systems, as long as it's kind of non-interacting, meaning quadratic system, is now very well understood. So we wanted to understand what happens if you put in many body interactions. What happens to those various phases, for example. And one way to sort of mimic many body interaction, you basically at every site of the quasi-periodic lattice, you attach the so-called probes, where you impose conditions that there are no currents flowing, and this effectively mimics many body scattering within this lattice, and you try to understand what happens to various phases that you have in a so-called non-interacting quasi-periodic system, and you start to see this environment or probe-assisted transport in this kind of systems. Okay, so now let's talk about the first setup where I'm having a quasi-periodic lattice and bringing qubits and trying to read out the qubit. Okay, so what is, but before that, let me just quickly introduce what is this quasi-periodic lattice, and I'm going to focus on two specific types of lattices. One is this AH, the Aubrey-Andre-Harper model, and another is a GAH, which is generalized Aubrey-Andre. So what is a general Hamiltonian? It's a fully quadratic Hamiltonian, which has some on-site term and the hopping term. So hopping is J, but I'm putting J to be 1, but we'll keep also it as J. Now there is this interesting on-site term, which has this lambda, which is going to be important, alpha, that is also important, and then there is this B. Now this B is supposed to be an irrational number. If that is the case, then your lattice becomes perfectly quasi-periodic. I mean, it's not at all going to be periodic, and you can't define really a unit cell. It doesn't repeat its pattern. That makes it quasi-periodic. B is irrational. Now there are two sort of cases that you can, two different types of model that you can have starting from here. So one is the situation when alpha is 0, that you call the Aubrey-Andre-Harper model, and if you keep this as very general, like with alpha, then it's called the generalized age. So what happens? Okay, so this is fully quadratic. You can talk about single particle states, and that's essentially given by this equation: single particle energy states and the eigenstates. So AH model is alpha equal to 0, so you only have the numerator. That's what you call AH. What happens is that, as I said, because it's neither periodic, neither disordered, you see a delocalization to localization transition. So if your lambda, which is this, is less than the hopping strength, then you see all single particle states are extended, which is given this red sort of, this is the site number, and it's kind of delocalized. This is very much like a close to periodic, what you expect for periodic lattice. On the other hand, if lambda is very strong, if this on-site potential term is very strong compared to the tunneling, you see immediately localized state. So this is the delocalization to localization transition, and lambda equal to J or lambda equal to 1. Remember, J is putting 1, all single particle states are critical. So you see a transition at lambda equal to 1 from the delocalized to localized states. So that's your AH model. On the other hand, if you put if you now turn on the alpha, that becomes a generalized version. Now this is even richer sort of a setup where you now have a so-called mobility age, which you can analytically find. And this is the sort of an expression for the age, mobility age. And what does that tell you? That you have the mobility age energy somewhere, and below that, given that these parameters are positive, below that all states are, it's in energy now, all states are delocalized or extended, and above that all states are localized. So this is what the generalized age offers you. So now we'd like to understand that these properties by reading out the qubit. Okay, so you have the lattice, which the Hamiltonian I just mentioned, and now I just bring a qubit and I couple it in a particular site of the lattice. So this is this H is the quasi-periodic lattice. You have the qubit, and this is how the qubit talks to the lattice. Okay, and the Hamiltonian I just showed you, which is the quasi-periodic. So right away, what you could do is, certainly since it's quadratic, you can diagonalize it. These are single particle states with the eigenfrequencies. And now the most important thing that you should remember is that when you're going from this C to the K representation, you have this ACE matrix, which is taking care of or telling you how the states of for each K are sort of varying with I in the real space. Okay, so this ACE is going to be important, and that going to modify this so-called coupling. When you're doing this transformation, is going to modify just this coupling. So this coupling, effective coupling, going to give you the information about the single particle states that you have. It's very plain and simple. And in this diagonalized representation, there is nothing but a simple spin-boson dephasing model. So from the qubit perspective, what you're really having is like an environment, which is this quasi-periodic lattice, and you would now just want to read out the qubit and see what happens. So it can be exactly solved. Okay, so what is the initial condition? So you prepare your system, the entire system in some product state of the system, and you put your, so let me see. Yeah, so here the system is the qubit, and you put your quasi-periodic lattice in some thermal state, but it's not necessary. You can put it even, it can be 0 temperature. But the most important stuff is this, where because of the symmetry that, this sigma z and here is a sigma z, what you can show is that the qubit population doesn't change. So the entire information gets encoded in the off-diagonal elements of the density matrix of the qubit, or rather the coherences. Okay, so what you could say, there's interesting dynamics that happens at the coherence, and if you don't have the lattice, the coherence will just oscillate with their own frequency, which is just this factor. But now, because there is a lattice which is interacting with, there is this exponential minus gamma I. So this gamma I is essentially what is the information that is getting encoded into the probe. And this gamma you can solve, and you see this GKI, which is essentially carrying the information of the underlying single particle states. And then there are this oscillatory factor. So remember K1 to N, K are all the modes that you have in the lattice. So now this is what you get. Okay, so, and we would like to understand what this quantity behaves when the system is in localized or in delocalized, or it's in at the critical, what really happens. Okay, so once again, the Ki is important. And this gamma you can split into the two parts. One is a vacuum contribution, meaning zero temperature. Another is a thermal contribution. The temperature doesn't really play a substantial role, so we can simply just look at the vacuum component. So this alpha K is this whole quantity without the temperature. Okay, so now let's see the results at least for the single qubit. So this is the gamma T that I'm plotting. Remember, the gamma T is appearing in this exponential. So if you're in the lambda equal to 0 or lambda 0.5, which is lambda less than 1, so that is delocalized. So all modes are extended in your lattice, and you are looking at this gamma of T. So this blue is what representing the delocalized case, where you see it's a small oscillations and finally it saturates. The reason is that there is this summation where all states are contributing, and as a result, you have finally these oscillations getting damped out. So that's the delocalized. And you see a remarkable sort of a difference when you are in the localized, let's say 1.2. So that is in the localized, and you see crazy oscillations, which is undamped. It doesn't get damped. Okay, so you clearly see a difference when the system goes from delocalized to localized. One way to think is that when your system is localized, it's like your qubit is just talking to one mode, one site particularly. It doesn't get sort of averaged out, and you see just two oscillator exchanging sort of information, if you like. It doesn't get damped. So there is a clear sort of a difference between delocalized to localized, and critical point, which is the green, is somewhere in between. And that you can characterize also through this so-called like an inverse participation ratio. So here you can also define this so-called participation ratio in terms of this GKI, remember. So GKI you can very easily characterize, or the PI, that if you're in the delocalized is perfectly, you could see it has a scaling which is 1 by n. If it is localized, is n raised to 0. If it is critical, it goes by n raised to minus b. So it really tells you that, okay, you are reading out and you are getting completely different signatures when you are delocalized or localized through a single qubit by reading out the gamma. Now, what other way you can actually characterize? Yeah.
Sorry, just one question. So in the previous slides, when in the gamma of at the critical point, no, the previous slide. So at the critical point, okay, there is somewhat smaller oscillation.
Yeah.
But apart from that, it's not a very clear signature.
There is no such clear. So it's like in between somewhat, yeah. But there's still oscillations, yes.
But can you do some Fourier transform and then do some analysis to get some exponents that, because something very special is supposed to happen, right? At lambda equal to 1.
Well, it's AH, so it's like all states are critical.
Still, I mean, in fact, it should definitely, something special should happen here.
Okay, right? So we didn't really investigate that point in detail. Maybe, yeah, maybe we can, okay. There are still some signatures I'll show you, like when you put 2 qubits, for example. Okay. There's some more detailed information that you're gonna get. So
okay.
Maybe
when you say critical, do you mean this power law bounded, power law?
Sorry, Professor Dutta Gupta, yeah, again.
When you say critical, you mean the power law, right?
Not really. So this is critical in a different sense. I mean, where all the single particle states are delocalized. So I'll come to that. I'll just come to the 2 qubit scenario. At that point, I can address that question. Okay, so another way to characterize, how the system behaving in these 2 different delocalized and localized phase is the so-called the non-Markovianity measure. So what is the non-Markovianity measure? So you see, there's this exponential minus gamma t. If your system, I mean, if the qubit is coupled to a bath and the bath is fully Markovian, then you're supposed to have a completely exponential damp of this. Okay, but if you have oscillations, which is essentially like non-monotonic, then this kind of rise in the oscillations sort of tells you that there is a non-Markovianity going on, which essentially people in the information science sort of think of like Markovian is like information leaking out throughout from the system all the time. On the other, non-Markovian is like some information is coming back to the system. So that essentially is what reflects to this oscillation. So if you define your non-Markovianity measure, where essentially you invoke the condition that this gamma dot t is less than 0, that essentially tells you that there are these non-monotonic features, then you can cook up this non-Markovianity measure, and that very nicely sort of tells you that, okay, if you're in the delocalized regime, then all modes are participating, and is kind of quickly takes you to the steady state for this gamma. Whereas if you have this localized phase, there are this crazy oscillation. As a result, the non-Markovianity measure is quite high, and that's what is clearly kind of differentiates between these two regimes. Okay, so that's like with a single qubit. That's what the readout. Yeah.
What's the kind of time scale? That's in what unit?
So here I put in J. So J is 1. So okay, so now what happens if you put two qubits at two different locations of your lattice? What is the motivation? The motivation is to now understand the underlying transport that you can have. Okay, so this is a non-local probe for transport. So what is the question that you're asking? That let's say these are uncorrelated at time t equal to 0, and there is some underlying dynamics that will start, and these two qubits will now get coupled at some time t, and through this correlation, you would like to understand what transport that happens. So another way, usually, like if you treat only this to be as your system without the qubit, you study transport by, by putting some localized wave packet within the lattice, and then you see how it evolves. And that is typical way to characterize transport, where you see how the width of the wave packet sort of spreading with time. So if it is, let's say, so there is a t raised to eta. If eta is 1, you call that is a ballistic transport. If it is 0.5, it's diffusive. And if it is eta equal to 0, you call it a localized transport. So that is the usual way of characterizing transport in an isolated system. But now we'd like to understand that through the qubits by bringing two copies of that. So what is the underlying Hamiltonian? It will be very similar, but now two copies of that getting coupled at different sites, I and j. Okay, so that's Hamiltonian, and you can similarly do all your algebra. And the central quantity that we are interested in, this correlation of sigma minus I, sigma plus j. I and j are different lattice sites, and you would like to compute that, and that also you can analytically solve. So there are various terms, but I just want you to pay attention to this so-called delta omega plus minus, which also is not very important. That's the Lamb shift that you get because you have now two qubits. They're getting sort of exchanging information. And then the most important term is this correlated dephasing that you're getting by bringing these two qubits together, and that has this gki minus gkj. So that is the crucial piece here. And now you would like to see what happens, let's say for the AH. So far I'm discussing only the AH model, which alpha equal to 0. So if you look at this, well, lambda equal to 0. So this is like really like a periodic, in fact, or 0 or 0.5. So this is you're in the delocalized regime. So up to certain time, the correlation doesn't develop. So I put somewhere first qubit and somewhere else the other qubit. I see up to certain time the correlation doesn't get developed, but after that there is substantial correlation. And if you now plot this t star is the time when the correlation develops, starts to develop. If you plot that as I minus j, the distance, it scales linearly. Okay, and that's a hint that it's actually a ballistic transport. On the other hand, if you are in a localized regime, critical regime, lambda equal to 1, correlation develops, and t star, if you plot, now it scales with I minus j square. Okay, so it's a completely different scaling, in which you can call this a diffusive. On the other hand, if you are now in a localized regime, which is lambda greater than 1, and correlation going to take very long time to be developed, and of course is going to also depend on the localization length. So here we plot this covariance in the very long time, and what you see is that it's exponential. And from there you can actually characterize, in fact, this localization length just from this readout, which goes as 1 by log lambda. So if lambda greater than 1, it's finite, and lambda equal to 1, the correlation length is infinite. Yeah. Okay, so that's a good question. So for AH model, you put any I, any j, it doesn't matter. Let me see. Yeah, sorry. So this I, so this could be any I and any j. The scaling will not change. Scaling will not change. Some tiny properties here and there will change, and that is what the generalized AH will show you actually where you put going to matter a lot. Okay, so now let's talk about the generalized Aubrey-Andre-Harper model, which has this mobility age. So what we look at here is the how we are plotting fraction of localized states that you have in this model. So you see these two lines. Now below this line, all states are delocalized. Okay, and below this line, all states are localized. So there are essentially no mobility age here. But in between now there are this mobility age where you could have certain states localized, certain states delocalized. So this is what you have. Now you would like to sort of map this through the qubit readout. Okay. So now if you get this correlated the gamma that you have, that you can get that information through qubit, and now you can easily construct what is the non-Markovianity measure, and you see almost similar looking sort of a. So you are trying to map this thing through the readout, and you're almost able to map. You see that the non-Markovianity measure is small when there is a delocalized. It's very quite substantial when it's localized because there is a back and forth oscillations. And in these regimes, because you have a mixture of delocalized and localized, now depending on what fraction localized and what fraction delocalized, you will get different signature. And as a result, which side you couple your qubit, you see there is this difference. It doesn't differ much in these two regimes, but here there is a bit of a difference because fraction of localized and delocalized states. Okay, so with mobilities, you have a side dependence of this non-Markovianity measure. Now, once again, we have the same setup, generalized age, and we put two qubits and try to understand the correlation. And so here, a plot for I equal to this and j equal to this, and it's at a different qubits placed at different locations. So these two are for two different locations, and you once again see differences because of the underlying fact that there is a mobility age. So here, what you see is that in the localized, once again, the correlation time, the correlation to get developed between these two qubits is exponential with the distance. So that we understand from the age. Whereas here, there are always some states which are delocalized, and as a result, that is like the fastest moving state, and it just determines the time scale. So the correlation that time to get developed correlation between these two qubits gets determined completely if you have even a single delocalized states, let's say. So as a result, within this entire regime, you have T star going with I minus. Whereas if you look at anywhere at this line, you have some critical states, critical and localized states. And now, since localized state doesn't participate, the critical state is going to take over and give you I minus j square kind of scaling. So, and the other observation is that since you are, there is a mobility age, because where you put your qubits, your signal is going to be different. So here is the more clear sort of a picture that if you are anywhere in this regime, you are essentially gonna get linear scaling. Whereas now, if you look at the plus point, the plus is here or here. It doesn't matter. Along here, there are some critical states that you have, and as a result, you get this I minus j square, or for example, even here or here, because there are fraction of critical states that you have. And so, essential point is that if it is localized, it's exponential. If it is even if there is a very tiny fraction of localized states that going to win and give you I minus j square, whereas in delocalized, all states going to participate and give you a linear scaling with the distance. Yeah, so mixture of critical and localized states essentially going to determine this. Okay, so this is sort of the first part. So what essentially we try to sort of do here is to read out without looking at really the lattice. We just want to see if we bring a qubit, what information we get out of it, and it kind of sort of gives you quite a bit of information just by reading out the coherence element of the 2x2 matrix. Single qubit, you get very nicely what localization, delocalization. The critical point might be still not very well resolved. But two qubits, at least in terms of if you're sitting at a critical point, the correlation time that it takes, the time takes to develop correlation, that kind of tells you that there are critical states that are lying there. So two qubits transport property, you get quite rich sort of thing here. And this kind of thing also can be experimentally implemented. That's what our hope is. The kind of future prospects that we have in this direction is that we incorporated dephasing sort of coupling between the system and the qubit. You could generalize this problem by not only having dephasing, but let's say a dissipative kind of coupling, which is like sigma x. Instead of having sigma z, you could have sigma z, sigma x coupling, and that might give you some more information. The other thing that we didn't sort of study here is a back action of qubit on a chain. So we right now looked at what chain does on the qubit and read out, but the back action of that is something that is still not really done and something that we could think for future. Okay, so since I have 4 minutes, I might just very briefly tell you about the second sort of a topic. where now I have this quasi-periodic lattice, which is not isolated, but is connected to two baths. And let's say they are at different chemical potential. So you will have some current, and let's say there's some steady state current. And since I showed you the Hamiltonian, which is fully quadratic, this model you can exactly solve and get understand what is the transport properties, which we essentially read out through Qubit in the previous problem. So here is a nice phase diagram, which was from this work, which was done with, by Archak, Manas, and Abhishek. So here, this is the quasi-periodic lattice, and the non-interacting one connected to left and right reservoir. And you have this alpha and lambda, which is basically your quasi-periodic parameters, the generalized age. And you see this nice phase diagram. In fact, this is the phase diagram that we kind of got through the Qubit in an isolated scenario. But here now, if you put the baths, you can talk about the current. And what happens is that in this whole regime of, because there were delocalized states, you see current scaling with N0. It's like a ballistic transport. Whereas here, all states are localized, you get exponentially localized current scales with exponential minus n. Where here in this whole critical line, there are some critical states, and as a result, you get 1 by n squared, which is a subdiffusive scaling. And if you walk along this line, that is essentially your AH, because AH you take alpha equal to 0, and only lambda equal to 1 is the critical point, where you also have a subdiffusive scaling. So this is now well understood, this phase plane and this quasi-periodic model, non-interacting. So we wanted to understand what happens if you now try to include some many-body interaction. And one of the effective way to do that is essentially, by the way, before that, I just wanted to highlight that this kind of transitions that you saw from going from delocalized to localized through a subdiffusive sort of a transport. So this we recently with Manas and Arshak and Madhumita, we put up, like we sort of understood in a slightly different context through there's some exceptional point in a non-Hermitian matrix. So if you're interested, please take a look at this. But let me now jump into what we did in this project. So in order to understand many-body effects, we brought probes which couple to each lattice site. And what does these probes do? It just makes sure that there are no currents that flows between this probe and the lattice. Okay, so it effectively kind of doing some phase randomization for the electrons that are coming from left and flowing to the right. Okay, and you ask the questions and effectively mimics many-body interaction. You ask the question, what happens to the transport properties? It's as simple as that. So if you look at here, now what is the gamma? The gamma is basically the coupling that you have between the probe and the system. So if gamma equal to 0, there is no probe. So that's like your non-interacting problem. And what you see is this blue sort of curve for the conductance. And you see that there are gaps. The spectrum has gap. So as a result, at those energies, you will see no transmission or no conductance. Whereas in other places, you will see significant sort of transport. These vertical lines are the band edges of your lattice. If you go outside of the band edge, then you know it's exponentially dying. The conductance is almost 0. Okay. But now if you start putting the coupling, turning on the coupling, so meaning you are now bringing the probe and making the coupling stronger and stronger, you first of all see that all this gap regime where there was no transport, now there is a finite transport. That is the first observation. And also outside the band, when there was no transport, what this probe did was to bring transport into it. So this is what we sort of call environment assisted sort of transport that is happening here in the delocalized. And similarly, you see in the localized. And in the localized, you almost see no transport. You see the magnitude here is very, very tiny. But the moment you now bring probes, you could start having sort of transport in this. And interestingly, that's not the only thing, but you actually see nice scalings. For example, in all this no transport regime that you had in the coherent case, when you put probes, you start seeing transport. It's not that it is happened arbitrarily, but it actually scales with the coupling strength between your system and probe. So when there was no transport, you see as you increase, so the question you can ask, can I just increase the coupling? Can I make this coupling strong and always see enhancement? The answer is no. The conductance increases to certain point with this probe coupling, but then it decreases. So you don't win all the time. You win up to some critical value of gamma. And interestingly, what you see, the way it increases is gamma 4, and it decreases as 1 by gamma 4 after some critical value. So this scaling one can actually show. And for large coupling, if you bring these probes and make this coupling very strong, you could immediately show that the underlying conductance, the entire phase plane that I showed, the transport in all regions becomes completely diffusive. Okay, so and diffusive is indicated by when conductance scales as 1 by n. So that also you can very clearly show. So this happens in all the regimes, and this is what I kind of displaying here, that the conductance now scales with 1 by n. When you have sufficient gamma, if you put in, and as a result, the chemical potential profile becomes linear. Let's not get into that. And even in the critical regime, you have, without the probe, you have n raised to minus 1.4. But if you put the probe with sufficient coupling, you get 1 by n. So the entire regime becomes diffusive. Okay, so with that, let me now sort of summarize this part. So there is this environment-assisted quantum transport that you now see. Your spectrum was gapped, but now as a result, you put the probes, you see environment-assisted transport at all regions where there is no transport. And that doesn't happen arbitrarily, but there are scalings with the probe coupling. And for sufficiently strong coupling, you would expect a completely diffusive sort of transport at all regimes. So with that, let me thank you for your attention. Happy to take any questions.
What kind of coupling do you have between the lattice and the path?
So these are like normal tight binding kind of coupling, like a very standard bilinear kind of coupling I can have, just like this term. Just like a quadratic sort of very standard coupling. So electron hopping and hopping out. So for example, here, all this is doing is that electron, like the quadratic term essentially tells you that there is electron hopping in and hopping out. But now, because these are probes, the condition that you impose that on an average, there should not be any net current between this.
Okay.
Any other question?
So when that slide you are showing, we are transitioning from the delocalized to localized by changing the lambda.
Lambda, right.
So the coherence time was changing from quadratic to exponential.
From linear to exponential via quadratic. The quadratic was right at the lambda equal to 1.
Why this is so? Is it due to the dephasing mechanism?
No, this is because the underlying states that are carrying the current, let's say, the underlying states are very different. Because in the delocalized, it's like the states are completely delocalized. So it's like faster. I mean, you could like, the correlation could develop much faster. Whereas if you're in the localized, I mean, there's nothing to spread, sort of, right? And critical is in between. So if you see right in the beginning, the plot that I showed, if you look at the states, the main physics lies in the underlying single particles states that you have. Yeah, here. So this is what makes the whole difference, right? I mean, you have states which are completely extended like block waves if you have periodic lattice. On the other hand, you have completely localized, and this essentially determines the time scale for the correlations to develop.
Quadratic term is in between lambda equals to 1.
So that's essentially lambda equal to 1, which is, you see, this particular state is very crazy. This is critical. This is like neither delocalized, neither localized. So that's why you get a.
Another question is that Hamiltonian you are showing. Can we think this as a generalized form of the Hubbard model Hamiltonian?
No, because it's fully quadratic.
It has a tunneling term. It has a interaction term.
No, but the Hubbard model, usually you have a beyond second order term, right? You could have U, N1, N2, yes, or Ni, Nj, but that term is not. So it's fully quadratic. So
lambda parameter is kind of doing this on
lambda is just changing your on-site potential. So if you look at this figure, if you look at here, so what lambda is the strength, but if you look at this cos 2 pi bn, b being irrational, you see this quasi-periodic lattice is like the period never gets repeated. I mean, you can't define like a unit cell, like, I mean, the lattice is not periodic. So it never gets repeated because you make that b irrational. If b was rational, then after some lattice site, I mean, you will get the pattern to be getting repeated. But because it's not, you now nicely see delocalized. If it was random, then you don't see the delocalization to localization transition in 1D at least. It's just completely Anderson localization. But now it's a
yeah. Thank you.
Bijay, I have a couple of questions. First one is a classic example of this Fibonacci lattice. This quasi-periodic lattice is a Fibonacci lattice.
Yeah,
some beautiful scaling laws, self-similarity, and other exciting features.
Yes. And
long time back, about 2-3 decades back, there are reports of weak localization in optical systems, of course, and then corresponding solid-state system that was weak localization, not the Anderson localization. nowhere close to Anderson localization.
Right.
I believe that your thing, what you are talking about, you must be having this weak localization. Nowhere close to the Anderson localization.
Maybe, but right. I mean, Fibonacci is another type of quasi-crystal where, you know, all states are critical and there are very nice scaling that is there. Something that we haven't looked at, and me and Prasanna were in fact few days like we're just talking about that. So maybe we could actually look at what, again, a similar problem, but with the Fibonacci, like what really happens there.
No, the question is regarding that. You are going to do scaling laws. Do you have similar scaling laws in this case? And there, the main result was in the band gaps. You'll be having the localized states. In the edges, you'll be having all the bounded states. That's why, and those states are all critical at the edge. And then, of course, at the open edges, you'll be having this extended states.
I believe so. I believe so. A similar kind of scaling, you should be able to even get there. That's my.
And what about self-similarity, multifractality?
That is there in Fibonacci. So at those, not fully sure.
Do you see any multifractal features in your model?
The multifractality feature, at least for the generalized AH at the critical line, right? I mean, there could be some multifractality. Sure. Yeah. So the critical line physics, the only thing that we could, at least in this work, were able to show was the time. I mean, the scaling with the time for the correlation to get developed, and that was just the square of the distance.
Last question is, in Fibonacci, you have this magic number.
Sorry.
Very important role. This is the last question. Magic number. Do you have any analog of this magic number in your quasi-periodic system?
Sorry, can you please repeat the question again?
There is a magic number which you call the magic number for any Fibonacci lattice. You can calculate a magic number. So something very peculiar happens at those magic numbers.
Right.
Do you have an analog of that magic number?
No, I mean not at least for these two models. I mean this is slightly different than Fibonacci. Yeah.
Let's thank the speaker.
Thanks.